Hello everyone, hope you are all doing fine. Welcome back to another lecture on electrostatics. In this video, we are going to learn about what is an electric dipole. We will define the electric dipole moment as well. In addition to that, we will also derive the electric field intensity on the axial line of an electric dipole, and we will also derive the electric field intensity on the equatorial line of an electric dipole. Okay, so yes, my name is Vijaykrishna and you are watching the UpPhys channel. Let's get started. Okay, first let us understand what is an electric dipole. Okay, the name itself indicates there will be two poles. The term poles means they will have equal amount of charges with opposite polarity. With opposite polarity. For example, electric dipole. Okay, so this is one charge and this is another charge. These two charges must be of equal magnitude. Let's say this is minus q and this one is plus q. Minus q and plus q. These two charges are of equal magnitude but of opposite polarity, separated by a small amount of distance, which is often represented as 2l. Okay, which is more often represented as 2l. You can even take it as d, r or l also. Okay, right. So two equal amount of charges separated by a small distance is called an electric dipole. Let me give you an example. For example, there is an element called, a composition is called NaCl. So this is formed due to Na plus and Cl. If I separate this NaCl into two ions, Na plus and Cl minus, this is positively charged and this is negatively charged. These two charges are separated by a small amount of distance is called an electric dipole. An electric dipole. So how do we define this electric dipole? What is an electric dipole? Two equal charges separated by a small distance is called an electric dipole. An electric dipole. An electric dipole. So this is how an electric dipole represented. Now coming to the next point, that is electric dipole moment. Electric dipole moment. Electric dipole moment. How do we define this electric dipole moment? This electric dipole moment is usually represented with p, small p. Okay. Now this dipole moment, electric dipole moment especially, electric dipole moment is a vector quantity. So it will have direction as well as magnitude. Direction and magnitude. Now coming to how do we find the magnitude of the dipole moment, of an electric dipole. So dipole moment is represented by P. It is defined as charge, any of the charge, magnitude of charge in the dipole, magnitude of one charge from the dipole into separation between the two charges, This gives the magnitude of an electric dipole. Of the electric dipole of dipole moment of an electric dipole. Clear? Let me define this one. So electric dipole moment is defined as the product of one of the charge in an electric dipole and the separation between the two charges of the dipole is called electric dipole moment. This formula gives the magnitude of electric dipole moment. Now coming to the direction of the dipole moment, always represented from negative q to positive q, negative charge to positive charge. When you look at this diagram, let's say this is minus q and this is plus q, separated by a distance 2l, then the dipole moment direction will be like this. Dipole moment direction will be in this direction, minus to plus dipole moment. Is that clear? So as dipole moment is a vector quantity, it will have both magnitude and direction. The magnitude of the dipole moment can be determined by using this formula, q into 2l. What is q? One of the charge in the dipole, and what is 2l? 2l is nothing but the separation between the two charges. Separation between the two charges. Q into 2l gives the magnitude of the dipole moment. And to find the direction, we have to identify the location of negative charge, location of positive charge, and we need to draw an arrow from negative to positive to showcase the direction of dipole moment. I hope this point is clear to you, right? If you want to give me an example, let's have an example here. So I'm going to take it off. Okay. Okay. Let's have an example here. Okay. Now here we have example. I'm saying here we have minus 2 microcoulomb charge, minus 2 microcoulomb charge, and here we have 2 microcoulomb charge separated by a distance, let's say 1 nanometer, 1 nanometer, 1 nanometer. Now what is the dipole moment? Dipole moment is equal to charge, one of the charge, 2 micrometers means 10 to microcoulombs means 10 to the power minus 6 coulombs, into separation between the two charges is 2l. 2l is nothing but 1 nanometer. You don't need to multiply with 2 because this entire length is given as 1 nanometer. That means 2l is directly given as 1 nanometer. So 1 into nano in the sense 10 to the power minus 9 meters. So what will be our answer? 2 into 10 to the power minus 15 dipole moment. Okay, let me define the units here. So what is the unit of charge? It's coulombs. What is the unit of separation between the two charges? Which is meter. Coulomb meter is the unit of dipole moment. Coulomb meter is the unit of dipole moment. Hope the example is clear to you. I'm going to give you one more example, little better than this one. Okay, so the unit, yeah, here I'm going to write it, unit of dipole moment is coulomb meter. Coulomb meter. Okay. Now let's find the dimensional formula. Dimensional formula. Dimensional formula. How do we find this dimensional formula? Coulomb. I mean, the charge is not a fundamental quantity. Rather, it can be expressed in terms of fundamental quantity, which is I into T. Q is equal to IT. I is a fundamental quantity. T is also a fundamental quantity. So the dimensional formula of Q is AT. Dimensional formula of Q is AT. And dimensional formula of 2L is length. It's nothing but L. ATL is the dimensional formula of dipole moment, right? Now once we are done with this example, let's move on to the next example. Okay, right? Okay, now let us suppose, so this is x and y axis. Okay, here I have placed let's say minus 2q charge, minus 2q charge, and here I have placed plus q charge, and here also I have placed plus q charge. Let it be. And this distance is a. This distance also a. Let it be. Okay. Now the question is asked to find what is the net dipole moment. What is the net dipole moment? Both magnitude and direction. Magnitude and direction. Magnitude and direction, because it is a vector quantity. It is a vector quantity. I am going to represent it as arrow. So we need to find the magnitude as well as the direction. Okay. First, What is the, I mean, how do we represent? Do we have two dipoles here? Yes, we do have two dipoles. I can split this entire 2q charge into one minus q and another minus q. One minus q and another minus q. The total charge is minus 2q. Now, can I represent this entire diagram? These two charges as one dipole, these two charges as one dipole. There are two dipoles. So first thing, this minus q and plus q will have dipole moment p in this direction. Okay, and again this minus q and plus q will have the dipole moment in this direction. Is my point clear? Let me explain it again. Okay, as we have the total charge minus 2q here, I have divided this minus 2q charge into two equal charges, minus q and minus q. One minus q is contributed to this dipole, another minus q is contributed to this dipole, the vertical dipole. Okay, now the dipole moment is always from negative to positive, so the dipole moment is towards the right, and this dipole moment is from negative to positive, this dipole moment is vertically upwards. So the angle between these two dipole moments is 90 degrees. 90 degrees. Now what is net dipole moment? P net is equal to P1 square plus P2 square plus 2 P1 P2 cos theta under root, right? P1 is P, P2 is also P, 2 P1 P2 both are P, so 2P square cos theta is 90 degrees. Theta is, this entire term will be 0. So what do I have? P square plus P square, 2P square. We have the root. So root 2 P, dipole moment P, is nothing but P net. P. So this will be the net dipole moment. Net dipole moment for the given arrangement of charges. Given arrangement of charges. Hope this example is very clearly understandable, right? If it is clearly understandable, let's move ahead and discuss the next, very important concept. Okay, right. Now, electric field on the axial line of a dipole. Electric field on the axial line of a dipole. So where do we have the dipole? This is our dipole. Let us suppose this is minus q charge and this one is plus q charge, separated by a distance 2l. Separated by a distance 2l. Okay, and what is the question here? The heading here is to find the electric field intensity on the axial line. Let us consider a point somewhere here. Somewhere here. We are going to find the electric field equation at this point. At this point due to this entire system of two charges, dipole. Okay, right. Now, now let us assume this point is exactly how much distance away? R distance away from the center of the dipole. From the center of the dipole. R, I mean this point. At this point only we are going to find the electric field. So this point distance from the center of the dipole is R. How much is it? R. Now, if this distance from the center of the dipole to the point is R, then what is the distance from positive charge to this point? It will be R minus L. R minus L. Let me explain it. If this is the center, then this distance will be, what is it? L. This distance will be L, right? And how about this one? Again, this distance also will be L. Total together 2L. If as this is the center, this distance will be half of this total length, and this distance will also be half of this total length. So this is L, and this is R minus L. R minus L. This is the distance that we are looking into. So this total distance is R. L is to be taken out. So R minus L. And what will be this distance? Distance from negative charge to point. It will be R plus L. R plus, hope the distance quantities that I have represented in the diagram are very clearly understandable, right? Let's move ahead. Okay, so I'm taking the electric field at this point due to positive q charge will be in this direction. It will be in this direction, right, because electric field always points away from the positive charge at the point of interest. Our point of interest is this one, so field is away from the point charge at the point of interest. The arrow mark is this direction, so this will be our electric field intensity due to plus q, that is to the right. Now this negative charge also creating certain amount of field at this location, so that field will be to the left, to the left. Okay, so why it is to the left? Because electric field always points towards the negative charge, so negative charge is here, the field must be pointed towards the negative charge. The electric field due to minus q is to the left. Now I'm going to write the magnitudes of electric field due to plus q and due to minus q. So electric field due to plus q is equal to k q by distance r minus l whole square, minus l whole square. Now I'm going to write the equation for electric field intensity due to minus q charge, which is k q. I have already told you I'm writing the equation for the electric field intensity magnitudes only, so k q by r plus l whole square, right? Till now it is, everything is clear, right? Okay, now as these two fields are pointing in opposite direction, what is the net field? E net. E net. E net is equal to rightward field, I am taking it as positive, leftward field I am taking it as negative. So E plus Q minus E minus Q. Right? Now E plus Q is how much? KQ by R minus L whole square. KQ by R minus L whole square minus E minus Q is KQ by R plus L whole square, KQ by R plus L whole square. Clear till now? Right. Now I'm going to take the KQ common, KQ, and we have R minus L square, R plus L square. In the denominator, R minus L square, R plus L square. If R minus L square is here, then R plus L whole square minus, as R plus L whole square is here, then R minus L whole square, whole into, right? Okay, now let's simplify this one. E net is equal to KQ is there, KQ, and we have in the denominator A minus B into A plus B, A minus B into A plus B. I'm going to write this one as A square minus B square into A square minus B square, right? So R square minus L square into R square minus L square. That means R square minus L square whole square. R square minus L square whole square. Clear? Right. Now, if I simplify this one, R square plus L square plus 2RL minus R square plus L square minus 2RL. If I multiply these three terms with negative sign, this R square plus L square minus R square plus L square gets cancelled. What do we left with? 4RL. 4RL. If you solve it, you'll get it. Okay, 4RL. So this is the resulting equation that we have got. So this is the final answer. But anyhow, we have the approximation here, right? What kind of approximation? While defining this electric dipole, I have mentioned that two equal amount of charges with opposite polarity are separated by small amount of distance, like I've given the example also, Na and Cl separated by nanometers distance, maybe picometers distance, maybe femtometers distance. So it is very small, the distance is very small. If the distance is very small, if the value is 0.0001, then if we have spared that value, then it will be 0.00000001, right? So the value will still be, going down. So that's why I'm taking R is very much greater than L. L is very much less than R. Then L square almost tends to 0. L square almost tends to 0. Then E net is equal to K Q 4RL. This 4RL, I'm writing it as, this 4RL, I'm writing it as K and Q. This 4L can be written as 2L. I'm taking another 2 here, okay, and we have R here. Is it clear? Now, in the denominator we have R square whole square, that means R to the power 4, because L square tends to 0, as L square tends to 0. So 1R gets cancelled. What do we left with? R cube. So the final expression for the electric field on the axial line, can I write axial instead of E net? E axial, okay, is equal to 2K. What is Q into 2L? This is the definition that we have already learned. Q into 2L is the dipole moment of the dipole. So dipole moment, I can written it as P by RQ. So this is the exact result that we are looking for. Okay, so this is the electric field intensity on the axial line, 2K P by R cube, where P is the dipole moment of the dipole, K is the Coulomb's constant, which can also be represented as 1 by 4 pi epsilon naught. R is the distance to the point from the center of the dipole, not from any of the charges. It is from the center of the dipole. Okay, clear? Right. I have already told you this dipole moment is a vector quantity. Dipole moment is a vector quantity. So electric field is also a vector quantity. So in order to represent this E axial, in which direction E axial is pointing? As we have got positive, it will be pointing in rightward direction. That means it is positive. It is positive. As we know, the dipole moment of the dipole, I am drawing it here. So this is minus Q and this is plus Q, separated by a distance 2L, and we have considered the point here. At this point the electric field is E axial is acting. E axial is acting. As you can see, the dipole moment of the dipole is pointing from negative to positive. This is P. This is P, and the electric field is pointing also from negative to positive in the same direction. That means here, if I represent vector notation, then it will get vector notation as well, because dipole momentum and electric field both are in the same direction. Or even you can even write the dipole moment unit vector notation here, as this is a unit vector quantity, unit vector whose magnitude is 1. When any quantity is multiplied with 1, the quantity will not be changes, rather it is introducing the direction along the dipole moment, that is also one way of representing it. Okay, but instead I'm directly writing the dipole moment here. Am I clear? Right? Okay, so this is a very good result, okay, right? Now let's move ahead, let's move on to the next. Right, now let us find the electric field on the equatorial line of a dipole, okay, right. Okay, now where is the dipole? Here we have the dipole. Here I have minus Q charge and here I have plus Q charge. Two equal charges of opposite polarity separated by a small distance. That distance is nothing but 2L. 2L. If this entire length is 2L, what will be this length? It is L. And what will be this length? It will be again L. Are we clear till now? Now, what is the distance to the point? What is equatorial line? Before all these things, we have to understand what is equatorial line. Equatorial line is the line that bisects the horizontal line equally. This dipole is this one, right? We are looking at equatorial line. That means this dipole is to be half divided. dipole length is to be half divided, that to perpendicular, that to perpendicular. This is what we call it as equatorial line. I have considered a point on the equatorial line. At this point I am going to derive the equation for the electric field intensity. Electric field intensity, let us see how. Okay, now what we are going to do is we are going to derive the equation for the electric field intensity due to individual charges at the point of interest. At the point of interest, as this is the positive charge, let us suppose the distance is r again. Distance is r from center to the point, from center to the point. In the earlier case also we have taken, if this is negative charge, this is positive charge, we have taken, this is 2l, and we have taken a point somewhere here, and this point is at a distance r from the center of the dipole, from the center of the dipole. Similarly, we have taken the distance to the point, distance to the point from the center of the dipole as r, as r. Okay, right. Now this distance is r. Now if this distance is r, now when you look at this right angle triangle, what will be this distance? It is r square plus l square under root, right? Now this also will be r square plus l square under root. Am I clear? Right? Okay, now let's move on to the next step. Okay, now let us find the electric field due to this positive charge, due to this positive charge at the point of interest. As we know, the electric field always points away from the positive charge at the point of interest. Our point of interest is this one, so electric field points away. Electric field points away like this. I'm naming this as electric field due to plus q. Electric field due to plus q. Now let us understand the direction of the electric field due to the negative charge. Negative charge is this one. Negative charge is this one. Point of interest is this one. Now let us find the direction of electric field. Electric field always points towards the negative charge at the point of interest. This is our point of interest. Towards the negative charge is this one. Is it clear? So this is E minus Q. E minus Q. Clear? Now let us write the magnitudes of electric fields due to positive charge and negative charge. Electric field K Q by distance. Distance is how much? R square plus L square root over square. R square plus L square root over whole square. Square and root will get cancelled. What are we getting? So K Q by R square plus L square. This is the expression for the electric field intensity due to positive charge at this point. At this point. Now electric field due to negative charge, I am directly writing this equation. KQ by R square plus L square plus L square, because root and square will get cancelled. In both the cases, the charge, the magnitude of charge is same, and the distance to the point is also same, unlike earlier case. Okay, so distances are same, so we are getting equal magnitudes of electric fields here. Okay, right. Now what I am going to do is, let this angle is theta. This angle is theta, and this angle also should be theta because of the symmetry. Because of the symmetry. When you look at this diagram, this length is L, this length is R square plus L square, this length is R, and this length is L, this length is R, this length is R square plus L square under root. That means these two are like triangles, right? Similar triangles. In such a case, this angle, all the three angles will be same for both the triangles. Okay, here theta, here 90, here 90, here what is it? 90 minus theta, here 90 minus theta. Clear? Right. Now if this angle is theta, then this angle also should be theta, right? Now if this angle is theta, then this angle also should be theta, right? If we have two lines, something like this, then I have drawn a line like this. If this angle is theta, this angle also theta. Same thing happened here. And if we have two lines, if I'm drawing like this, if this angle is theta, this angle also should be theta, right? So this concept is used here. Okay, so angles have been identified. Now electric field E minus Q is acting in this direction, E plus Q is acting in this direction. Two vectors are acting in different directions. So we need to resolve these two vectors into perpendicular components so that we can add them easily, right? Because electric field is a vector quantity, so I cannot add electric field directly, rather I can add them vectorially. To do so, I have to resolve the vectors into rectangular components, perpendicular components. Okay, now E plus Q component to this side is as theta here, E plus Q cos theta, E plus Q cos theta, because theta is here. Now to this side, E plus Q sin theta, E plus Q, E plus Q cos theta, E plus Q sin theta. Now look at E minus Q. E minus Q x component. That means theta is in this direction. So E minus Q cos theta comes here, and this vector to the down, E minus Q sin theta, comes to the down. Clear how I resolve the electric field vectors E plus Q and E minus Q into two components, right? Right. Now when you look at this, components, E plus Q sin theta, E plus Q and E minus Q are of equal magnitude. E plus Q magnitude is equal to E minus Q magnitude, right? After looking into these two equations only, you can say that, or else if you have enough knowledge on enough understanding on electric field vector representation of electric field, then you can directly tell these two magnitudes of electric fields are same by just looking into this diagram, right? Okay, so as the magnitudes are same, E plus Q is equal to E minus Q, sin theta are same, then these two components will get cancelled. That means the vertical components are being cancelled. The electric field at the given location is only or purely due to horizontal components. Because they are acting in the same direction, as you can see. Right? Now, E net. E net. At this point, E net is the sum of these two, right? So E plus Q cos theta plus E minus Q cos theta. We know magnitudes of E plus Q, E minus Q are same, so I can write 2 EQ plus Q. I am writing cos theta. Clear? Now, 2, what is E plus Q? KQ by KQ by R square, small r square plus L square, right? Okay, 2 EQ plus E plus Q cos theta. From this triangle, any of the triangle you can take. From this triangle, cos theta is equal to adjacent upon hypotenuse, right? So cos theta can be written as adjacent L by hypotenuse r square plus L square root over. This root can also be represented with whole power 1 by 2. Now let's simplify this equation further. So E net is equal to, this equation I am writing it as K Q into 2n, right? K Q, this 2 is multiplied here, 2n. Clear? Now r square plus L square whole to the power 3 by 2, r square plus L square whole to the power 3 by 2, because power 1 by 2 together 3 by 2. Clear? Right. This is the equation that we are looking at. Now let's use the approximation that we have already used in the earlier case, that is L is very much smaller than R. In such case, L square tends to 0. Right? L square tends to 0. If L square tends to 0, then E net, and I am already telling you this Q into 2L is nothing but dipole moment P. So I am writing the equation as K P by R square whole to the power 3 by 2. This 2 will get cancelled. Then E net is equal to K dipole moment P by RQ. This is the ultimate result for the electric field intensity on the equatorial line of an electric dipole. of an electric dipole, where P is dipole moment, electric dipole moment, and R is the distance of the point, from the center of the dipole, where K is Coulomb's constant, which can also be represented as 1 by 4 pi epsilon naught, as we all know. This is E net. Can I write E net as E equatorial? So let's write E net as E equatorial. So this is the expression for the electric field intensity on the equatorial line of an electric dipole. Clear? Right? Okay. Now, let us identify the direction. In the earlier case, if you can recall, if this is minus q and this is plus q, dipole moment is pointed in this direction. Electric field is also pointed in this direction, axial, right? Now, let's look at this diagram. Here we have, this is the electric dipole and our point of interest is this one, minus q plus q, Direction of dipole moment is from minus q to plus q. This is our dipole moment, but the net electric field is pointed in this direction, E net, equatorial line. Net electric field on the equatorial line is to the left, whereas the dipole moment is to the right. That means here dipole moment is in this direction, whereas the net electric field is in this direction for an equatorial case. Okay, so I can write E equatorial is equal to minus, if I want to write the vector representation, minus, what is it? Minus KPRQ. P vector can be written as like this, or you can even take P unit vector as well. Without taking the vector notation here, you can take unit vector notation here. That makes no difference. Okay, because P cap is the unit vector whose magnitude is 1. When 1 is multiplied to any quantity, the quantity will not change, rather it introduces the direction along the dipole moment. This is how vector representation of electric field on the equatorial line of an electric dipole. Clear? Okay, I'm going to take this off. Right? Okay. So till now we have learned about what is a dipole moment definition we have discussed, and we have derived the equation for the electric field intensity on the axial line of an electric dipole, and here we have derived the equation for the electric field intensity on the equatorial line of an electric dipole. We have seen two different cases, on the axial line and on the equatorial line. Now let us derive the equation for the electric field intensity for a general case. Not every time the question asks like find the electric field intensity on the axial line or on the equatorial line. They will ask the questions at certain angle also. Find the electric field intensity of an electric dipole at 60 degrees, okay, or at 120 degrees also. That also we need to solve. For that purpose, let us derive the equation for the electric field intensity at any random point. Okay, now right, electric field at a random point from the center of the dipole, okay. Every time we have been taking the distance to the point from the center of the dipole only, not from any of the charges. Just remember, I'm repeating this sentence just to remind you, okay, so that you won't have any confusion while using it in solving the problems. Okay, now we have the dipole here. One is negative q charge, the other one is positive q charge. Now the electric dipole moment is pointing in this direction, right? So this is our dipole moment, right? Now let us consider a point somewhere here. We need to find the electric field at this point from the center of the dipole, which is 0. Okay, and this, let's suppose this distance is r. Okay, and this position vector is at an angle is at an angle theta from the dipole moment, from the dipole moment, from the dipole, as you can see. Okay, right. This is how I have considered the system. Okay, now let us find the electric field intensity at this location due to this entire, due to this dipole. Okay, right. Now instead of taking the approximation, I am going to use the regular method, which can be understandable very easily. I am going to follow the simplest method. Okay, rather than taking the lines and all by using the approximations and all, I am going to consider the simplest method to follow. Right. Now, if this is the dipole moment and it is a vector quantity, I can resolve this dipole moment into two perpendicular components. Let us suppose I'm going to draw the line here. Okay. Now, like this. Okay. I've drawn the line here. Okay. Now, when you look at this dipole moment can be resolved into two components. One is onto this R, one is onto this perpendicular, right? Now, if I resolve this P into two components, we will get two components into these directions. In this direction, we will get P cos theta, and in this direction, we will get P sin theta. Is my point clear? Right? Now I have two dipoles. One is this one. This is one dipole, P cos theta, one dipole, and this is P sin theta, another dipole. There is no approximation at all in this method. Okay. So P cos theta is one dipole, P sin theta is another dipole. Okay. Now, as P cos theta and R along the same axis, can I consider this situation as electric dipole and this point is on the axial line? I'm going to say the statement again. I'm going to reiterate the statement again. This P cos theta is one dipole moment of one dipole, and P sin theta is dipole moment of another dipole. This P is not existing here. Now this P is resolved into two components. Now this P is nothing but P sin theta into this direction, P cos theta into this direction. Now P does not exist. Take it out. Okay. Now this P cos theta is along the R, right? Now when you look at the first diagram, I mean this minus Q, this plus Q separated by distance, and the point R is along the axis only, in this case dipole moment is P, R is on the same axis, Can I consider that situation here? That situation and this situation are similar, except this dipole moment is P, here the dipole moment is P cos theta. Right? Now, okay. Now let us write the equation for the electric field intensity on the axial line. For this dipole moment, it is axial line. E axial is equal to, what is the dipole moment E axial? 2K, sorry, not Q, 2kp by R cube, right? I'm going to write the same equation. 2k p is nothing but P cos theta here, so I'm writing P cos theta by distance is same, R cube. Okay, R cube. Okay, this is for horizontal axis, that is axial line. Now let us look at the perpendicular line. As this is one dipole and R is perpendicular to this dipole, so this dipole moment and R, this system can be considered as, can be considered as a similar case of electric field along the equatorial line of a dipole, right? Now, as we all know, minus Q plus Q, and this is perpendicular bisector, okay, equatorial line. Now the point is here, the net electric field is in this direction, E equatorial, whereas Dipole moment is in this direction. As I have already told you, electric field and dipole moment are opposite to each other. We have written the equation also, right? Now, as dipole moment is in this direction, as dipole moment is in this direction, the electric field due to this dipole moment on the equatorial line will be opposite to the direction. This one, whereas opposite to the direction. Now, E equatorial is equal to, what is E equatorial? Kp by R cube. Kp by R cube after the approximation. So K, here P is nothing but P sin theta. I am going to take P sin theta upon R square. Upon, sorry, not R square, upon R cube. R cube. So this equivalent equatorial line electric field is acting in this direction. Axial line electric field is acting in this direction. Let's write this. Okay, this is here. E equatorial is equal to K P sin theta by R cube by R cube. Okay, by R cube. Right? Now, these two electric fields are acting at right angles, right? When you look at this diagram. Now, to find, I'm going to take this entire thing off. Okay. Now, to find the net electric field, E net is equal to, as both of them are acting at right angles, E, what is it? E axial square plus E equatorial square under root. Right? Now, E axial is how much? 2 kp cos theta by R cube. 2 kp cos theta by R cube whole square plus E equatorial is kp sin theta by R cube. Kp sin theta by R cube whole square. If you simplify this equation, we have common terms. Kp by R cube, squares are there. If I take it out, Kp by R cube, square and root cancels. Okay, and we have 2 cos theta square, that means 4 cos square theta, and we have sin theta square, that is sin square theta, right? And we have root as well. Okay, now this Kp by R cube, I can write this 4 cos theta as 3 cos square theta, 3 cos square theta plus cos square theta plus sin square theta, root over. This cos square theta plus sin square theta can be written as 1. So what am I getting? Kp by R cube 1 plus 3 cos square theta. Okay. 3 cos square theta plus 1 under root. This is the equation for the net electric field. At any random point. Due to a dipole. Clear? Now, as electric field is a vector quantity, the magnitude can be determined by using this one. Okay. Now, let us find the net electric field direction as well. Okay. Let us suppose the resultant electric field is acting in this direction at an angle alpha. Okay. Now, at an angle alpha. Right? Now, this is E net. To find the direction E net, what am I going to do? Here I am going to write. Okay, what am I going to do? Tan alpha is equal to E perpendicular by E parallel. That means E equatorial by E equatorial. Axis perpendicular to the axis is this one only, no, E perpendicular by E parallel. E perpendicular is how much? E perpendicular is Kp sin theta by Kp sin theta by R cube by E axial. E parallel is 2 Kp cos theta by R cube. And this R cube cancels, Kp cancels, 1 by 2 remains, 1 by 2 sin theta by cos theta is tan theta, we have tan alpha, tan alpha. So you will not be asked to find the direction of the net electric field from the axial line. You may be asked to find the net electric field direction from the dipole moment. From the dipole. In such a case, what is the angle? What is the angle? This theta and we have alpha. Total angle. Sorry. And so angle from dipole moment P vector. Dipole moment P vector is theta plus alpha. Theta plus alpha. What is alpha? Alpha is equal to tan inverse 1 by 2 tan theta. 1 by 2 tan theta. I hope all the steps that we have followed till now are clear. Are clear. Now we will have the comparison as well. Okay. So all the steps, the explanation that I have followed, I think everything is clearly understandable. If you're still unable to follow, please comment below. Okay. Right. Now let's move ahead. Okay. Let's do the comparison. Compare axial and equatorial. Compare axial and equatorial. Compare quantity. Okay, compare, I'm taking it as heading. Sorry. Compare. Okay, quantity. Quantity. Okay. Now quantity I'm taking axial line. Dipole moment. Dipole moment. Negative to positive Q, negative Q to positive Q. Okay, that is minus Q plus Q P, minus Q plus Q P. Clear? Now, electric field. Electric field E axial is equal to 2 Kp by R cube, E equatorial Kp by R cube. Okay, that means E axial is greater than E equatorial. E axial is equal to 2 times E equatorial. Clear? Now, direction. Magnitude we have discussed. Now coming to direction. Direction. So E axial direction along dipole moment. Dipole moment. Okay. E equatorial. E equatorial is opposite to dipole moment. Dipole moment. Okay. So these are the basic differences, or maybe not even similarities are there. So these are the basic differences between electric field on the axial line of a dipole and electric field on the equatorial line of a dipole. Hope the lecture is clearly understandable. If you really find the lecture is helpful, please do like, share and subscribe. Don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. So that's it in this video. Thank you for watching. See you in the next